So today, just a quick video about a project that I've been working on over the past few months, which of course is in the HackTV space. Now, HackTV is a project which I covered pretty thoroughly back in my 11th video. Now, you will recall from that video that I was a bit disappointed with the quality of the signals that could be generated with it. Now, this is not entirely the project's fault. The main problem, unfortunately, is just the availability of good quality hardware to actually realize the signals which HackTV generates in software. So some time ago, I decided to embark on an effort to try and create a new piece of hardware which would allow better quality signals to be generated. So let's have a look at the present hardware options for turning the signals which HackTV encodes or generates, depending on your preferred terminology, into actual real analog signals. Now there's two main classes of device at the moment. There's the RF option and there's the baseband option. Now the RF option, of course, is the HackRF one, and this is probably the most well-known and arguably best and most convenient way of working with HackTV. This gives us an RF output, so we can feed it straight into the antenna socket of a television, which is certainly convenient for more vintage models. Now, back in the HackTV video, I looked at this in detail. There was all kinds of imperfections. We have noise, we have images, we have spurious tones, we have all sorts of nastiness coming out of this, and it was just such a mess that I personally couldn't really even be bothered trying to delve into all the problems and trying to understand them. But that all having been said, the output of it is perfectly usable. You can plug it into your TV, you'll get a pretty nice picture. So from that perspective, is it a problem? Not really. Now the other option here is what they refer to as the FL2K. Now this is a USB video VGA chip which you can find in some USB dongles like this one. The HackTV devs worked out that they were able to get raw access to the DAC in that chip. Well, there's actually three DACs because there's RG and B, and you could use them to generate some kind of video signal. They're high bandwidth DACs, so yeah, they're certainly more than sufficient for use with HackTV. Now the problem with this device is that, well, this is a VGA dongle. The impedances, the basically electrical characteristics of the output on this is fundamentally not suitable for use with composite video or analog television. You don't have the right reconstruction filters on here either, and it might, on top of that, just be a rather mediocre chip. I'm not actually sure, but yeah, this is not really a very great option either. So yeah, there's your two options. Certainly both usable, I would say, but not really all that great. Now it's worth taking a minute to talk about how we got here, because it's been a bit of a story. Back in my 17th video, I talked about sound and syncs, which is a system for encoding audio into the sync periods of analog video signals used for distribution within broadcaster networks. Now, some years ago, I was talking to Phil, the lead developer of HackTV, about building sound and syncs into HackTV. The assumption back then was that we would just have to reverse engineer the equipment that we could get our hands on in order to actually figure out how it worked and implement it. But since I uploaded my two videos on this, we now actually have the full documentation for the system, so we can actually just go ahead and implement it without having seen any of the equipment whatsoever. And certainly Phil doesn't actually have access to any of it. And with that, HackTV suddenly had one of its most eyebrow-raising features ever, along with all of the other eyebrow-raising features that it has. Now, myself and another owner of some of the only surviving decoders immediately tried to test it, and we just couldn't get it going. Now, Phil was pretty certain he had implemented it correctly, but for whatever reason, it just wasn't working. And certainly looking at it on the oscilloscope, the signals were just pretty nasty, noisy, and it's like, yeah, this is not going to work. Now, pretty quickly we realized the problem was, of course, the hardware which is generating the signals, not the software implementation. So that was how I got onto this. It was just that desire just to see this most obscure of features actually working. And if I could build a device which did that, then I think it would probably have a whole lot of other uses. So how might we build such a device? Well, as the video title would suggest, we're not proper television engineers here, we're just hackers. Now, as a bunch of hackers, we need some inspiration, and what better inspiration than this cranky old Power Plus decoder, which we talked about in more detail back in video number 14. Now, a quick reminder, the architecture of this box is that we take an analog composite video signal in, we turn it into a digital signal, We muck around with it a whole lot inside of this ASIC, and then we convert it back into an analog composite signal, and also S-video as an added bonus. Now when you look at this, it's pretty seductive looking because we have this digital bus going in one end and we have an analog signal going out the other, and this must be exactly what we want, right? Well, not quite. Now when we look at the details of it, we find that this chip internally does the sync generation, chrominance encoding. These are all things that HackTV already does in software, and we don't really want this chip doing it for us. Then if we fed the input that this thing wanted into it, we would lose a lot of the functionality in HackTV, which we don't really want. But it does have some benefits in that it has a digital oversampling filter, only 2 times in this case, and probably not quite enough filtering on the output after that, but anyway, that's another subject. And certainly this type of chip, there's a lot of chips like this out there. This is probably one of the earliest examples. There's a ton of others made by various manufacturers. Unfortunately, they all pretty much follow the same script in that they take digital RGB or YUV input and they expect to do everything internally, which we just don't really want this. What we want really is the output of an arbitrary video signal generator. To find that, however, we need to start looking inside of video test equipment. Now this here is the output of a Phillips PM5655, and I believe this came to market in 1993. It's one of the earliest things that I have to hand, which I think is worth looking at for inspiration. Now the architecture of this is pretty different to what we were just looking at before, so instead of that consumer video encoder we have 2 DACs. Very nice, very high quality DACs here, 16-bit. And there's 2 of them. One is for luminance, one is for chrominance. The outputs of these are summed together and fed into this really nice analog reconstruction filter. That's amplified, and then it heads to the connectors on the rear. So as I say, this is much nicer arrangement, a lot more flexible, because instead of having this magic chip doing everything for us, you can have this really raw access to these DACs. But it's not really exactly what we want for HackTV, because of course there are 2 digital data streams which have to be supplied to these 2 DACs separately, which that's just not what we want. We really just want to have one. As a side note, the actual chrominance encoding in this one is done inside of this digital mixer here. This is a Raytheon part, very, very expensive chip. Quite specialized, but yeah, it's sort of doing a bit of what the Philips encoder was doing in that Power Plus unit, but as I say, it's a lot more powerful and a lot more flexible than that particular item. But yeah, this is, as I say, this is not really what we want. Now this is the Raden Farts SGF test pattern generator. This came to market, I think, around about the same time as what we just looked at. Now, this is a bit more like what we want. So if we look here, there's just the 1 DAC, analog reconstruction filter, and everything before the DAC is digital. So yeah, this is looking a bit more like it. Now, in terms of how this actually works, I'm not entirely sure. I don't have the manual for it, and I don't know of any surviving copies of it either. But in the spec sheets, there is a mention of some magic chip they have for doing the chrominance encoding, and I think this might be it here. This is a mystery chip, some kind of gate array device of some sort, which is taking probably YUV components from the proms and somehow encoding them. So I'm not really sure how this thing works. Whatever it does, this is very much a private chip. It likes to be inside of its own metal box here, and it doesn't want to be bothered by any of the other surrounding components. But anyway, as I say, this is pretty much what we want, but we wouldn't build something exactly like this because this is a very legacy design. These chips here are just really expensive, so yeah, we don't really want to go down this path. But yeah, looking better. Now next up we have the PT8601. This is an ex-Philips item. It's a test pattern generator module for their SPG family, which we looked at in the previous video. Now this particular design actually has come to be open sourced, which is pretty convenient. I built the big brother of this from scratch back in video number 7, and we talked about this one in particular more in video number 8. It's of a very similar architecture to the Raden Farts SGF in that we have just a single DAC, an analog reconstruction filter, then straight to the output. So this is really the kind of design that we want for this item, and this one is rather more sensible than the Raden Farts, and it's all built out of off-the-shelf components. Pretty much everything from here onwards is still in production, so it's still very much feasible to build. It has a whole lot of other stuff on here, all sorts of digital circuitry. Well, HackTV will be doing all of this, so it's really just this bit on the end here that we want for our project. Now there is actually another architecture which you will find in video test equipment which was engineered from the 2000s onwards. I don't have an example to show you, so what we'll do is just quickly draw a diagram of it. So we have our usual digital bus coming from probably a bank of proms, and that then heads straight into an FPGA. And inside this FPGA we have a 4 times oversampling digital filter. Quite similar to what you would have in an audio application, although they generally go much higher. After that we have a DAC. Then we have a filter. Low pass filter. And there's our video output. Now this is a really nice arrangement because we have really the best of all worlds here. We have the low cost build of the consumer video encoder in that we have 4 times oversampling and the very minimal analog reconstruction filter at the end of it. But we also have the power of just having a DAC that we can just feed whatever we like into. And as I say, this is a very desirable arrangement. My project doesn't use this architecture because I'm not aware of any oven-ready open source example of an arrangement like this. If there was one, I would have taken it and used it, but there isn't. Maybe in future, if there's sufficient demand, we could look at engineering something like this, but as I say, at the present time, we're going to be using that PT8601 as our starting point. So the concept of this project is basically to just combine these two items together. And the reason I've done it this way is because, well, that's just a really easy thing for me at least to do. Basically, we're taking the output from this and whacking it on top of here. Now the output on here, as I say, is this 16-bit DAC, which normally runs at 13.5 megahertz. And it just so happens that this is actually a very comfortable operating frequency for the HackRF1. It can supply 16 bits of data at 13.5 megahertz pretty comfortably actually. It can do it up to just above 20 megahertz, but it's really sweating at that point. So as I say, you back it off to 13.5, it works pretty nicely. Normally that data would be fed into the DAC, which is underneath this shield here, but what we're doing is reprogramming the CPLD to route it to this convenient header here, which has 16 data bits and a clock signal on it. Very handy. I'm not sure what they actually put that there for, but quite convenient for this project. Unfortunately, it's not normally fitted for the HackRF1. Yeah, I had to solder that on there, but that's not really a big problem. Now this of course is the device that's going to be plugging into that header. Now notice that we have basically on the underside here headers which plug straight into these sockets on here as we would expect, and of course we can see the PT8601's output is faithfully copied onto this board. Now there is some extra stuff on here, power supply. We do need a dual rail power supply which has to be generated on this board from the USB supply voltage, but otherwise it's a pretty straightforward item. Now we have a couple of other niceties on this board. So this here is a dedicated sync output, and the reason we added this on here is because one of the problems we have with HackTV is how to actually trigger the oscilloscope, for example on sound and syncs when we've destroyed the sync pulse. It's a bit annoying and difficult to do. So at some point we'll get around to implementing a dedicated sync for this board. It's just a small change to the software. The other thing we've added here is a dedicated audio output, and this is another great advantage of using the HackRF1 because of course we have I2S inside this microcontroller here, which means that we can add a simple little DAC on here. And the reason that this is done is because one of the problems we have with HackTV when doing baseband video is lip sync on the audio. So typically you would use the PC sound card for an audio, but you know, the hardware and software stacks for the sound and video are all going to be very variable, so it's a bit difficult to get things in sync. So if we could do everything on the one piece of hardware, which is a sort of known quantifiable design, we can basically work it all out in advance and just make any corrections in HackTV itself and have a really nice consistent result. Now as I say, presently audio is not implemented, but in future we'll probably get around to doing that. Alright, so time for a quick demonstration of sound and syncs from HackTV. Now obviously we have the sys decoder here, but no coder because of course that's coming from HackTV. Now presently we're in the idle state. I'm just going to open the front panel here, and as you can see we've got a whole bunch of errors here because, well, there's no input signal. So I'll just go over and fire that up right now. So there we go. So we can see the decoder has sprung into life. We've got the system good LED on, which means things are pretty much all working. Now if we have a look at the oscilloscope, we can see the sys data burst, this time generated by HackTV. It's just so much better on this board than it was when we were trying to do it through the HackRF and through FL2K. It's just, I don't actually have any recordings of those experiments, but the data burst was just a complete noisy, unrecognizable mess, whereas now we can see this clear constellation. It's really, really nice. Now, it's not as nice as an actual real sys coder, but it's pretty good, and there's certainly scope to improve this. There are some changes to the software which could be made to the filtering to make that look a little bit nicer. Now, even though we're up and running here, you'll notice that we've got this LED flashing down here, and this LED, according to the legend here, says signal fail. So something isn't quite right. Now, if I actually plug in the speakers here and we have a listen to the sound that's coming out of this, you can hear there's a blipping noise which is occurring exactly in time with this LED flashing. So something is not quite right here. Now, at first I had a bit of a job trying to work out what the actual problem here was, because certainly looking at it on the scope it looks pretty clean. I actually discovered it by accident when I tried to genlock a PT5655 to HackTV, which is a thing that you can now do with this board. When I trigger this oscilloscope from that generator, we can see that we have some jitter coming from the HackRF. Now, if you trigger from the HackRF, the jitter appears to be coming from the 5210, but I think that the jitter is coming from the HackRF because it's just impossible that you could be getting that kind of jitter out of a professional generator. Now, having realized this, I thought I'd just try a little experiment to see if we can actually improve it. So what I'm going to do here is just heat up the clock generator chip on the bottom of the HackRF1 here, or from the bottom of the HackRF1. Now this clock PLL chip is something that's frequently complained about on the HackRF. It's a really cheap, pretty basic part which doesn't really perform very well, and it doesn't have particularly good jitter characteristics. But what I found is that they do actually vary with temperature. So if we actually just heat up the PLL chip a little bit, they'll start to change. And eventually, it actually works really well. Now you can see that we don't have any errors anymore, and we have the correct sound coming from HackTV. So yeah, that's just really annoying, but not really all that surprising, because as I say, this PLL chip is really just a real pain in the ass on the HackRF platform. I don't know, I mean, having this board, we could put a really nice RF grade PLL on it, you know, to get a more stable clock signal, but that's going to push up the cost of it quite a bit. I'm not really sure if it's worth it, but it's good to know that that is the problem at the very least. Well, I have to say, I'm thoroughly impressed with that. Phil basically implemented sound and syncs in HackTV purely from the manual. He's never seen any physical equipment. And when I tested it here, it works first go, no code changes whatsoever. Hats off to that. And now for that test we were inevitably going to do, and that's to generate a real Philips pattern with HackTV. And take my word for it, this is one of the hardest things to do when we're talking about software generating video signals in today's day. Now what we see on the screen here is not just an image of the Philips pattern nicked off Wikipedia and crudely converted to a video signal, which a lot of people do. This is the real deal. All of the signals from the original are all present and almost at the same level of quality that you would get out of a genuine generator. And it has taken a long time to get to this point. So without further ado, let's go up to the oscilloscope and actually have a look what we're getting out of this. So for this demonstration, I have the full length of cable in view, terminated straight at the oscilloscope, and this is just to show I'm not pulling your leg. This is definitely coming from this board. Now I'm going to stake my reputation on saying this is the highest quality realization of a Philips pattern coming from a desktop computer ever. I don't think anybody else has ever done it as well as this before, so this is a really exciting thing to see. Now what we're looking here is at the sync period, and straight away we can see just how incredibly clean these signals are. Now they're not as clean as a real Philips generator, but they're pretty damn amazing compared to what we're used to looking at from HackTV. Now if we actually scroll across here, we're going to have a look at one of the elements of the Philips pattern which you can't represent with a computer graphic, and this is why this is a really special demonstration. So we're presently in the center of the central grid here. Now notice these two patches of black here, they're at the same level as the neighboring boxes. Now if we just take our trigger down to the lines below, we'll notice that, just look at the level of the black here. It just falls a bit. It's actually gone below the black level. So this is now a negative voltage and a negative luminance. And as I say, this is not something that you can represent with a computer graphic, but it's one of the tests in the Philips pattern. This is called a plugge, and it's for setting the black level on monitors. We won't get into details about it today, but this is why this is just a really special thing to see. Now there's of course a whole lot of other signals which also can't be represented in a computer graphic. I'm not going to go into them all right now, but suffice to say we have everything here. Now, a big disclaimer here, HackTV is not generating the Philips pattern from fundamentals in real time. The samples that we're outputting here are originals that came from Philips, but the point is proven here is that we have this device which is able to turn computer-generated video signals into real, very clean video signals. And that means that HackTV's own internal software generation has a much better chance of being seen in its full glory. Well, that's all I intend to cover on this project for now. Where exactly it goes from here is not entirely clear. I think it will be very useful for me in the making of this channel, particularly if I want to talk about some obsolete video system where all of the equipment which encoded a particular type of signal has all been scrapped, or it's out of reach and HackTV happens to support it, or maybe it will support it in the future. This will be a fantastic way to demonstrate those systems in extreme levels of quality, so I think this will be really useful for that. I also think it will be useful for the HackTV developers to actually develop the project, and I will make sure that they get some samples of these boards. Whether or not this is useful to anybody else is unknown. If this is the kind of thing that you think you might like to have, let me know in the comments, and certainly if there is a lot of demand for something like this, it might be worth developing this into a more proper project, and certainly in a new form which would be a bit easier to construct, because in its current form, it has all of those inductors on it which have to be wound by hand, and the whole thing has to be tuned by a network analyzer. It's just quite hard and quite time consuming to construct. So as I say, I don't think it's feasible to be mass produced in its current form, but maybe a different form, like the oversampling example we talked about using an FPGA. If something like that were to be developed, as I say, it could be mass produced. But anyway, that's all I have to talk about for now. So yeah, as always, thanks for watching.